So, as we said, our friend Clausius discovers this new property. An amount of heat transfer divided by the temperature at which that heat transfer occurs is going to cause a change in entropy. Right? Now, I've just had to go grab me a cup of water here. Now this is cool water. I pulled it out of a refrigerator, and so as I remove heat from this water, we know that the molecules are they becoming more chaotic or less chaotic as I cool those water molecules down? Are they moving more predictably or less predictably as I cool them down? They're moving more predictably, correct? They're actually achieving a lower entropy. As I cool these water molecules down, they reach a lower state of entropy. Now I've pulled them out of the refrigerator, put them in the atmosphere. They're absorbing heat. So as these water molecules absorb heat, as heat is added to the water molecules at a particular temperature, they're increasing in entropy. But if I put them back in the refrigerator and I remove heat, as I remove heat, I will decrease the entropy. They will become more predictable or less entropic. So S represents entropy. Entropy can be changed by adding or removing heat to our system. If that heat is added in a reversible fashion, the amount of heat divided by temperature will give us the amount of entropy change. All right, so we're measuring entropy. Again, total entropy is designated as S, and that's true in almost all thermodynamics textbooks I've encountered. That has units of energy per temperature, and you can see that here, right? That is an energy divided by temperature, so this has to be energy divided by temperature. Absolute temperature, Kelvin or Rankine is just fine here. A lot of times, as you've seen in the property tables, we'll deal with quantities that are per unit mass. There's not, if you look at my S's here, right, my lowercase s looks a lot like my capital S. I try to make my capital S look large. Fair warning, my capital S will look like an integral sign. I don't know what to tell you. I'll try to differentiate those, but just you've been warned. So lowercase s is entropy per unit mass. Dimensions there are normally going to be kilojoule per kilogram Kelvin or BTU per pound mass Rankine. Those are the two major units that we will use to measure entropy. Okay? This is the second law. In its purest, ugliest differential equation form, this is the second law. Entropy is a quantity that is generated. It is not a conserved quantity. Well, it is actually if it's a reversible cycle. That's the best case scenario, is a reversible cycle where entropy is conserved. But in all practical applications, entropy is being increased. It's being generated. The second law tells us that we will always generate more entropy than the amount of heat transfer divided by temperature that we use to change the entropy. So the change in entropy will always be larger than the amount of heat transfer that causes that entropy change. We talked about cooling and heating up water to change the entropy. After we've cooled it up or heated it down, we will always experience a larger entropy change, unless we do it reversibly, which is really tough to do. But the reversible case is the limit. Now, again, this is the purest form of the second law. This is the form of the second law that we will use most of the time. So this is the entropy change for a system after an irreversible process, or after any process, honestly. It could be reversible in this form. Let's see if we can derive this. Let's say, so if we start with the purest form, we say, well, this change in entropy is always going to be greater than or equal to an amount of heat transfer divided by the temperature at which that heat transfer occurs. So ds is greater than or equal to dq over t. Now, let's not, again, I'm not assuming you've had differential equations, so let's just integrate both sides of this equation. Let's get rid of the differential. So let's integrate from state 1 to 2. ds. And let's say that's going to be greater than or equal to, preserve the inequality, and that's going to be greater than or equal to the integral from state 1 to 2 of this dq over t. Well, integral ds is just s, so that's s from state 1 to state 2. Is going to be greater than or equal to this integral, the total amount of heat transfer occurring between states 1 and 2 per unit temperature. Now, this is not too bad. This is for a process from state 1 to 2. For any process going from state 1 to state 2, the change in entropy is going to be greater than or equal to the amount of heat transfer required to get there per unit temperature. Or the total amount. That's an integral, a total amount. Okay, well, inequalities are okay. There's nothing wrong with them. They just, well, it's not an equation. A lot of times we like equations. We can actually convert this to an equation. That's what we have here. We can actually convert this to an equation, but we have to preserve the rules of the inequality. And this is normally how we present the second law. So we say the change in entropy is equal to this total amount of heat per unit temperature from state 1 to 2 plus the amount of entropy generated, where the amount of entropy generated is always positive, or at least 0. Okay? So this preserves the rules of the inequality. Here we're saying this is bigger than this. Here we're saying this is equal to this plus the amount that it's bigger. So we've preserved the rules of the inequality. This is the second law for a process from state 1 to 2. This is the common form of the second law that we will use. Now, we can work per unit mass, where we divide everything by m. Now, that's lowercase s's. Lowercase s2 minus lowercase s1 is equal to the integral of del little q over t plus little s gen. We can also work per unit time, where, here if what we've done is divide by mass, down here I would multiply by what? If this is entropy per mass and I want entropy per time, well, I would multiply by m dot. So I could say m dot times little s2 minus little s1, those are table properties I can go look up, is going to equal this integral del, let's say big Q dot, the heat per unit time, divided by temperature, plus, I'm just going to write big S gen dot, the rate at which entropy is being generated. Now, this is not three different equations. This is the same equation. I've just changed its bases. Here, this is total amount. Here, I've divided by mass, so every one of these is per unit mass. Here, I've multiplied by mass per time, so every one of these terms is per unit time. It's the same equation. Right? Notice that, please. This is all same equation. This is all the second law for a process from state 1 to 2. These are your fundamental equations. These are your primary equations you'll use in this chapter. Now, what the heck do we do with this guy? Steve, are we going to do partial integrals? No, we're not going to do any partial integrals. We'll talk about how do we deal with this partial integral thing over the next lecture or so. There's really two main possibilities. The main one, a lot of times, is there's just not going to be any heat transfer. A common scenario is if we're dealing with an adiabatic situation, this just goes to 0. There's another one where the temperature is constant, or we'll assume the temperature is reasonably constant, and then it's actually not too bad. So those are the main things that we'll do with this. Let's talk first about this entropy generated term. All right? So we talk about the entropy generated. This is page 2. So the entropy generated for a process The entropy generated represents the change in entropy for our system plus the change in entropy for the surroundings. I used my cup of water earlier, right? So I've got water here, and we said earlier I cooled this water down. I put it in the refrigerator and I cooled the water down. That decreased the entropy of the system. Now remember, we've said that this entropy generated can be, well, it can only be greater than or equal to 0. Okay? Now, so basically the rules are this. That's if the entropy generated is equal to 0, that's what we call reversible. If the entropy generated is greater than 0, we call this irreversible, aka normal. That's kind of expected. This is kind of the ideal case, best case scenario. If the entropy generated is less than 0, in theory this is impossible. Now really cool things happen if we can, this is what we call destruction of entropy. The opposite of entropy generation is destruction, right? So if we could destroy entropy, really cool things happen. I always tell students, if you figure out, if you estimate your entropy generated and you get a negative quantity, do me two things. One, double check all your numbers, check your units, make sure you are sure. And the second thing I want you to do is call me. Don't tell anybody, don't talk to anybody, just call me. Because we're going to do some really cool things if you can figure out how to destroy entropy. We're pretty sure you cannot. All examples everywhere we've seen in the universe tell us you cannot destroy entropy. Okay? So we said this was the rules, and what I brought my water in here earlier to say this. I can decrease the entropy of my system. That's okay. This can be negative. I can take my water and I can cool that down. I can decrease the entropy of my system. To do that, I have to increase the entropy of my surroundings. Meaning, if I put my water in a refrigerator, I have to make more entropy in the air around the refrigerator than the entropy that I remove from the water. That's what a refrigerator does. It removes energy and entropy from the contents inside and adds that heat and increases the entropy of the surroundings. The second law says if this is negative, this has to be more positive than this is negative. The absolute value of this has to be larger than this if this is negative. And vice versa. I can cool the surroundings down. That's what a heat pump does. A heat pump cools down the surroundings and then heats up the system, the house, to do so. Now, entropy is not heat, but they do go hand in hand. They are very much linked through the second law. Okay, what else here? So, yeah, there's the rules. Just wrote this here, right? Entropy, we call this entropy destruction. If it's negative, which we do not think is possible, best case scenario, we conserve the entropy. We just don't generate any new entropy. Okay, I think we're good there. Got an example. Let's see how I am on time. Good place to stop, and then we'll work an example real quick. All right, so loud pop.